Hey there, AP friends. Welcome to Chapter 3. And in Chapter 3, we're going to take the idea of the derivative and go forward full throttle. We're going to learn all the shortcuts. We're going to learn how to take derivatives of really cool things such as trigonometry and exponential and polynomials, but lots and lots of shortcuts. So basically, Chapter 3 is called Differentiation Rules. What are we allowed to do and how do we do it? Section 3.1 starts very basic. We're going to learn about the polynomials and exponentials. And some of you might have heard these shortcuts before, but they're going to save so much time. So now, instead of doing derivatives like this, the limit as h goes to 0 of f of x plus h, I mean, this is still useful. You can use it if you want, but the shortcut's going to take care of that and make it much, much faster. But in order to figure out the shortcut, can we just do a little pattern recognition? Can you see? When we've done derivatives before, as we took higher and higher derivatives, do you remember when we got to the derivative of just a single number, the derivative just ended up being 0. Don't let this notation throw you off, folks. Remember, this is just dy dx, but the y here is the function inside the parentheses. So that's dy dx. So the derivative of 2, the derivative of just any number, is always 0. Okay, how about the derivative of just a line? What's the derivative of x? We learned that derivative of just x would be just 1. And basically we noticed that as I took derivatives of polynomials, basically the derivative went down by 1 degree. So quadratic became linear, linear becomes a constant, and constant just goes down to 0. So take a look at the left-hand side here, folks. Can you see a pattern here? The derivative of 3x to the 4th is 12x cubed. Can you see what I did? How about the derivative of 5x squared is 10x to the 1 power? Negative 4x to negative 4th is positive 16x to the negative 5. All right, one more. How about 1/2 x to the 1/2 power is 1/4 x to the negative 1/2. Can you see what the pattern is? It looks like there's two things that we did. It looks like that we took the exponent that was on the x and we multiplied it in the front. That's how I got the 12. And then look what happened to the exponent afterwards. He just went down by 1. For polynomials, folks, this is what's called the power rule. This is your first shortcut of the year. Yay! So this is how you take the derivative of just a typical term in a polynomial. If this is just some x to the n power, you take the n exponent and you multiply it in the front. That's why you get this. And then your exponent just goes down by 1. So again, the exponent gets multiplied in the front. If there's a constant there already or a coefficient, you just multiply the coefficient by the exponent, and then you subtract 1 from your power. That's called the power rule. Probably one of the most popular shortcuts for derivatives that we have on the AP exam. All right, for example, now here's some examples, but their answers are already there. So I'm going to cheat for a little bit. I'm going to cover them up so you don't get too tempted to see them. All right, ready? Number 1, let's find the derivative. This is dy dx, where this is your y, dy dx. Okay, this is just a normal, straightforward polynomial. Ready? To take the derivative, power rule says, let's take the 3 exponent and multiply it in the front. That becomes 4 times 3 is 12. And then your power just subtracts by 1. This becomes x to the 3 minus 1. There you go. Man, that was easy. Okay, next one. 2x squared, the 2 exponent multiplies the front, multiplies the 2, and I get minus 4x to the, subtract 1, and I get 1 power. I'm not going to write the 1, but it is x to the 1. Now, just to make sure this works, okay, this is 1, but there is an x there. I don't know if you can see it, but he's kind of invisible because he's really 1 x to the 0 power. Well, let's do power rule if x to the 0 is there. Okay, ready? Let's multiply the 1 by the exponent, which is 0. Oh, look at that. He just goes away. That's why the derivative of a constant by the power rule, too, is just 0. So the derivative of 1 would be 0. Final answer? About 12x squared minus 4x. Let's check our answer. Wow, we're good. We're good. Wow, and there's number 1. That's the power rule. It's so pretty and so easy to use. Now, number 2 is going to trap you. This is dy dx. Our y is in the parentheses. Why can I not just do the power rule on this? I would love to. Hey, power rule, yeah. No, you can't do that. Why? Because he's a fraction, and that's called a quotient, and we're going to learn the quotient rule later, and that's very, very different. So we can't do power rule on this yet. Can you change this so it looks a little bit more like a regular polynomial? Meaning, can we break it apart? I used to call it this. I used to call it make a heart and break it apart, where I get to divide the top terms by the bottom term single. So I'm going to divide that bottom term into both terms like that. Make a heart and break it apart. Because I do that, look what happens. What's 2x to the 4th over x squared is just 2x. Subtract your powers. Cool. Next one, minus 9 x3 divided by x2 is just x to the 1. Okay, great. Now, let's take the derivative of that. Now we're ready, okay? I couldn't do power rule up here. Don't be tempted. We can't do it. So let's do power rule now. Ready? All right, here we go. The power, 2 multiplies the front 2, and I get 4. This becomes x to the, subtract 1, x to the 1. Okay? And then this one, 9x. Well, 9x is 9x to the 1 power, so we'll multiply the 1 in the front, and we just get minus 9. X to the, well, 1 minus 1 is 0. That's x to the 0. Remember, x to the 0 is just 1. So final answer is 4x minus 9. There we go. Let me make sure. Is that the same answer we have here? It is. Yay, we did it. Awesome. All right, number 3. Can you do the same thing to number 3 that we did with number 2, folks? Remember, we can't do power rule here because he's not a single polynomial. He's a quotient. He's a fraction. You must simplify first. Okay, why don't you do that? Pause the video and come back and check with me and see how good you are. Okay, friends, after we've divided the x cubed into both pieces, here's really what I'm taking the derivative of. It's going to really be 2x to the 1 minus 9x, but the power on the bottom was bigger, so I actually have a negative 1 power. That seems a little scary, but it's actually going to be okay. No biggie. We can do it. Let me make some room over here. Excuse me, friends. Coming through. All right, ready? I'm ready for power rule now that we simplified it. Okay, this is x to the 1 power. So the 1 multiplies the front, and I get 2. X to the, well, the 1 minus 1 becomes 0. Okay, that's going to be 1, right? Now, check this out. On the other front here, we have minus 1 as the power. Is going to multiply the negative 9 in the front, and I really get positive 9 x to the, now watch this. It's a negative 1, and I'm supposed to subtract another 1. So that becomes negative 2. Okay, remember, subtracting from a negative just makes it really more negative. The x to the 0 just goes bye-bye because that's 1, right? And I just get 2 plus 9x to the minus 2. And that's my final answer. That's the same thing as 2 plus 9 over x squared. Either one would be legit. Whichever you like is fine. Okay, so we can do power rule very easily, but if it's a fraction, you can't do it yet. Be careful. Also, what if by chance the actual things you're taking the derivative of are radicals? And remember, from way back in Algebra 2 land, if exponents are if exponents are rational, those are the same thing as radicals. So you see these radicals here, friends, and if I'm going to take the derivative and you want to use power rule, you have to change the radicals back into exponents. Radicals back into exponents. So you might need a little review of changing radicals back into rational exponents, fraction exponents. Okay? So on number 1, I see a square root. Square root is, that's a 2 type of index, and the x is being raised to the 1, so we can say this is the same thing as x to the 1 over 2. Okay, so I'm really taking the derivative of this, x to the 1 over 2. Ready? Can you do power rule? The 1/2 goes in front, and I subtract 1 from the 1/2. Does it make sense why you get this? The 1/2 in the front, and then 1/2 minus 1, excuse me, is a negative 1/2. We're good to go. How about the next front? How about this one? This again is a square root, but x to the 3 now on the inside. So that becomes x to the 3 over 2. Rewrite the radical as a rational fraction exponent. Power rule, ready? 3/2 multiplies the front. And I subtract 1 from the 3/2. How does that look? And finally, how about the last one? Okay, this one's a little tricky because, first of all, it's a fifth root, and it's x to the fourth on the inside, and the 4 is just hanging out here in the front. Well, let's just let him hang out there for a little bit. Let's not worry about him. But let's change this radical into that. That's x to the 4 over 5. And notice how the 4 just hangs out in the front. Okay, ready? Power rule. The 4/5 multiplies the front. That's 4/5 times 4 is, yes, 16 over 5. And when we take 4 over 5, we're going to subtract 1 from the power. And if you think common denominator, does it make sense why I get this? Okay, so I feel like we can do really power rule on almost anything. If you do it on a quotient, you have to change it back into a complete polynomial like we did for number 2 and 3. And if you have a radical, you have to change the radical into rational exponents before you do that. Sounds good? All right, you must memorize this, friend. It's one of the easiest derivatives ever. The derivative of the exponential function is the exponential function. The second derivative is the exponential function. The third, the fourth, the fifth. Every time you take the derivative of e to the x, you automatically get e to the x. Memorize, please. Because we're going to have a lot of formulas to memorize, it'd be great to make flashcards for this. Flashcards are a must. Okay, e to the x, just to figure out why this is happening. E to the x, remember, is exponential function, so he's a growth function like this. And if you think about it in terms of tangent lines, as I move left to right, and I think tangent lines, the slope of these tangent lines are really close to 0, so my derivative here in red, as I get higher, I get more to the right, my slope is more positive, well, look what I'm getting out. My derivative graph in red is exactly the same thing as the original. So the derivative of e to the x stays e to the x. That's beautiful. All right, ready for example? Let's find the equation of the tangent line. Remember that kind of question? To the graph of f of x equals this. Notice it's a mixture of polynomial and e to the x at the point where x equals 0. Okay, now remember, to find the equation of the tangent line, you have to find the slope first. And slope is the same thing as the derivative. At what a value or x value? Oh, 0 over here. Okay. So my slope is going to be the derivative at 0. So we need to find the derivative of f of x first. And instead of doing x plus h like we used to, we have a power rule. Let's do it. Ready? F prime of x, the derivative is, ready? 3x squared. Okay, the 2 multiplies the front. And this becomes x to the 2 minus 1. Good. The derivative of 2x, the 1 exponent hits the 2, and the x to the 1 becomes x to the 0, so that just disappears. So I'm just going to leave it like 2, if that's okay. So minus 2 plus, okay, well, the derivative of e to the x is just e to the x, so the 4 can remain out there constant. We'll talk about that a lot later too, friends, but whenever you take a derivative and you have a constant, you can just leave the constant on the outside, take the derivative of the inside, and then bring the constant back in if you want. Okay, so this becomes 4 times, what's the derivative of e to the x? My eyes are going up here. It's e to the x. All right, so there is your derivative. Look how fast that was. But now I want to figure out what is f prime at 0. Let's find out what the actual slope is at x equals 0. All right, when we plug in 0 for x, we get 6 times 0. Remember, I'm plugging it into the derivative. All right, let's see. That's 6 times 0. That goes by. And I get minus 2 plus, well, e to the 0 is also just 1. So that's just 4 times 1. I get negative 2 plus 4, which is 2. Yay. Okay, that's my slope. Great. Now I'm missing something else, right? I need the equation. I think I've got the x value. I need the y value. How am I going to find the y value? We plug it back into the original, right? So let's try to find out what is just regular f of 0, right? Here, plug it in for x. Okay, that means all these x's are going to be 0. This x is 0. And this is e to the 0. All right, well, 3 times 0 squared is just 0, minus 2 times 0, plus 4 times e to the 0 is 1, so 4 times 1 is just 4. So when x is 0, y is 4. Okay, friends, we've got our point. We've got our slope. I think we're good to go. Ready? Let's put this in easy green. How about y minus the y value equals slope times x minus the x value. There you go. If you want to, because it's x minus 0, you can also leave it like this. Either answer is fine. The AP will take both. But please, 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 super please, don't change it in the slope-intercept form, because in case you make a mistake, you will lose points, even though you got the original right. So just leave it and walk away. Great job on that, friends. So tangent lines are really, really useful, but actually in real life, we can also include what's called the normal line. Now, normal lines are really cool, despite the fact that the name of them is kind of dumb. It's just normal. But what that means is, if you're given a curve over here on the bottom left, here's your f of x, and I draw a tangent line, it's going to touch the graph at only one point. There's our tangent. Okay, in physics and in other kind of science problems, we need what's called the normal line, because that's how the forces will work, such as centripetal and centrifugal forces, are usually normal to the tangent line, which means it is perpendicular. So the normal line is always perpendicular to the tangent line. Okay, that means we're going to have to remember a little bit about perpendicular lines and the slopes. So here we go. Let's try to figure out the normal line here, in case you got that, is perpendicular to the tangent line at that point of tangency, which just means right here on the graph, at the point where it's tangent, the normal line goes straight through that and is perpendicular to the tangent line. All right, let's try it. So now, let's ask for another equation of a line, but here I'm asking for the equation of the normal line at this graph here, at this point here. Okay, well, it does bring back the idea. Do you remember, friends, from geometry, perpendicular slopes? For example, if you know that one slope is 3 over 2, what's the perpendicular slope? Remember what we said? It's the opposite reciprocal, or I call it, you flip and you make the opposite sign. It's called flopposites. It's flipping and opposites. So perpendicular slopes are flopposites. Or if you just think negative reciprocal, that's fine too. Okay, so your job is, you actually are going to find the tangent slope. Not the tangent line, but go and find the tangent slope m, just like we did before. But then before you make the line, go and find the normal slope, therefore. Change it using your flopposite, and then you can make your equation. All right, so that's a good order to go in. Let's find the slope, meaning derivative. Let's plug in and get an actual number. Find the flopposite slope, and then we can make your equation. Okay, so first thing again, let's just find the derivative, because we need to find the slope. Here we go. I love power rule. Here we go. Ready? The 4 is going to hit the 1 over 4 and die. And I just get 1. X to the, let's subtract power. By 1, you get 3. That was cool. Minus, can you see? How about 4x to the 1? Do you see by power rule? Plus the derivative of 3/4. Remember we learned the derivative of a constant is just 0. Awesome. So really, if I erase that part, my derivative is really, really here. But now let's find out what's the actual slope. Oh, I should put a derivative sign there, Mr. Brown. Lazy. So what's the derivative at, what's my x value? 1. Let's plug it in. What's the derivative? What's the slope at 1? That's going to be 1 cubed minus 4 times 1. 1 cubed minus 4. Okay, great. So that's my tangent slope. My tangent slope is negative 3, or you can think negative 3 over 1. So if the tangent slope is negative 3 over 1, what's your normal slope? Remember, it's perpendicular. So it's a flopposite. It should be positive 1 over 3. Great. Okay, so we got the m value that we need. We got our normal slope. We've got our x value, but again, I think we're missing the y value. So how are we going to find the y value? Yeah, let's plug this into our OG function there. We get f of 1 is 1/4, 1 to the 4th, minus 2 times 1 squared, plus 3 over 4. All right, let's simplify. Let's bring him over here. There's a little more room. F of 1 is, how about 1 to the 4th is just 1, times the 4th. 1 squared is 1, times 2, and then plus 3/4. Now I got some beautiful fractions here. I've got a 1/4 and a 3/4. That's 4/4, which is just 1. And so I'm just left with 1 minus 2, or negative 1. Okay, so over here on the right-hand side, when x is 1, the y is -1. Ready? Final answer to this question is, what's the equation of the normal line? Here we go. Y minus your y value is -1 equals your normal slope here. Not the tangent slope, but the flopposite. That's 1/3 x minus, and what's the x value plugged in? Was +1. If you want to change this negative to a positive. That's great. So it'd be therefore y plus 1 equals 1/3 x minus 1. And that's the equation of the normal line to that graph at the point 1, -1. So derivatives are so much easier now, friends, using the power rule. Isn't that great? So the power rule helps, again, if it's a polynomial. So if it's not, you have to change it. For example, if it's a quotient, like we had for number 2 and 3, you have to change it so it's a normal polynomial. If it's a type of radical or root, you have to change it using rational powers. And then please memorize the fact that the derivative of the exponential is just the exponential. Easiest derivative ever. And then we ended with the normal line, which is just the perpendicular to the tangent line. So think flopposite slopes. Hey folks, that's the end of section 3.1. Pretty cool, huh? I'll see you next time.